All right, good afternoon, everyone. So we arrived last time to, what did we do last time? Yes? Raise your hand. Now we need to give everybody the same opportunity to answer. Yes?
About diffusion current and drift current.
That's good, that's good. So, what's the diffusion current? Anyone has an idea? Yes, the one in the back. Yes? Yes? You? Yeah?
Diffuse from high concentration to low concentration.
Very good. So what's the cause of that diffusion current? What makes it? Who creates it? Who is the responsible about it? Yes, go ahead. No. No comment, please. If it's wrong, it's wrong. So, who knows? Yes? Yeah, it's the concentration. But what about the concentration? What makes the concentration create that current? Anybody knows? Yes, again? No. That was an example only. That's not really the cause. That's just an example. In the slide, that was an example. Anyone? Yes? Very good. That's the gradient. Now, what we mean by a gradient, it means the variation of the concentration. Okay? The variation of concentration. Means if the density or the concentration, they are the same thing. If it is not constant, there will be diffusion. That's what it means. You understand? Good? You have to take notes. Okay? Now the other current is what? She's drift and then? Drift current. The diffusion we finished. Now, drift. Who caused the drift current? Or what's the cause of the drift current? Raise your hand, please. Yeah? Was that electric field? That's right. That's good. So if there's an electric field and there is a free carrier that is moving around, that electric field will move it around. And that will create a current called the drift current. Clear? Very. Now, we come to an application of what we have studied last time, and here we are in week number 2, second class, last class of this week. So, in here, we put all this into application. By doing what? By bringing two semiconductors, P-type semiconductor and N-type semiconductor, and bring them together. Just let them touch each other, okay? Good. When they touch each other, at the point of touch, that touch point, we call it a junction. A junction. Junction, it means where a place, it's a coordinate, a place where two different things come to meet. There is many junctions. There is a crossroad junction, there is, etc. There are tons of applications in real life where you find junctions, okay? Two things or two roads come together to a certain cross-section, and that's called a junction. Hatta in the road codes, it's called also junction, okay? Good. So now we have a junction, we call it PN Junction, okay? Because that's a place where the P-type and N-type semiconductors, they meet. Okay, good. So, what else? We start to give names. Why? Because we are going to play with this. We call it device. This is what? A device. What is a device? It's اختراع. Device comes from the word to devise. To start and making imagination. It's like inventing. So a device, وليد اختراع إذا حبيتوا تسموها literally, okay? It's something that we made it. But we are talking about electrical devices. So this is the very basic device that we can have in microelectronics, and that is called a PN junction device. We later on give it another name, and that's a diode. Okay? It's exactly the same, but a little bit of it's exactly the same. If you take it literally, it's exactly the same. So this is on the diode, it's the same thing. But here when we mean by PN junction, we are talking mainly about this interface. Now, the side of the P-type, we call it anode, terminal. Because this side, we need to connect it somewhere, if we need to connect it. And that connector is called anode. We put here a metal contact, and we make sure that this metal contact is connecting to this semiconductor. Okay, we call it anode, and this side, we call it cathode. That's it. We know now our device. Bingo. All right, let's keep going. All right, I need to plug this. Okay, good. So let me do that because we need to get this going. One second. All right. So, okay, that's fine. So let's see. Bingo. Good. All right. Thank you very much. So what happens when we create a PN junction? So before we said that, first we are going to study this junction without connecting it to see how it is, what's happening with that junction. So when we bring this PN junction together, when P-type and N-type together, what will happen really? What will happen? So basically the P-type semiconductor, what does it have? What's the majority of carriers there? Holes. Very good. And the N-type majority are electrons. What we are meaning, we are always talking about carriers that are free, not that are bound. Bound we are not interested because they don't help in the conduction to create a current. All right, so first and foremost, before even anything happens, we know that the P-type has majority of holes and N-type has majority of electrons. But is the N-type negatively charged or positively charged? N-type semiconductor is positively charged or N-type negatively charged or positively charged? N-type semiconductor, huh?
N-type,
No, I'm talking about the whole material, huh? The N-type semiconductor. Is it positively charged or negatively charged? Negatively charged. Who said negatively charged? Raise your hand. Sah, who said this is positively charged? What the others they say? What?
It's not charged.
It's not charged. But again, N-type semiconductor is N-type. It has 3 carriers. Yes or no? So, is it charged or not charged? N-type and is not charged? What's going on? So, we'll explain that in the next slides. And yes, it's not charged because we did not really change the charge. And let me show you that in this graph. I should have put the graph a little bit earlier. And the graph is like this. So basically what happens is that the P-type semiconductor, as you can see here, this is the P-type, right? So what you see here in big circles in here, these are the holes. And who generate the holes in the P-type? They are coming from where?
Donors.
Who say donors? Raise your hand. So acceptors? Very good. It's actually acceptors. Yeah, you see? Acceptors create the holes. Yes or no? So when the acceptor creates a hole, what does it do? It will steal, right, an electron from another silicon and bring it to create a bond with a neighbor silicon. Yes or no? Very good. And it will become negatively charged. Yes or no? Because it did not have that electron. Yes or no? So now, after stealing that electron, it becomes what? Negatively charged. So these negatively charged, these are the acceptors. Okay? Now the acceptor has created a hole, but it becomes what? Negatively charged. Very good. But the total charge is what? Is 0. We did not change it. Did we change it? No. The acceptor came without any extra charge. It just created a hole from somewhere and became what? Negatively charged. So if you add the positive with the negative, boom, it becomes what? Neutralized. So the hole that we have created in here, it will still go around what? Go around these, the acceptors. Yes or no? Because the positive charge and negative charge. Yes or no? Do you understand? So because there's always this eternal motion, that the hose is going around and, you know, the acceptors are there. So they don't neutralize themselves, but still we say that these holes are basically covering these acceptors. So these acceptors, they have like a cloud on top of them, of holes, to make everything what? Neutral. Okay? So every single acceptor in here that is ionized, is still neutralized by a hole that is close by. Okay? So, it's not negatively or positively charged. It's still neutral. The same story happens with the N-type semiconductor. Okay? As you can see, now the electrons in the N-type semiconductor are made by whom? Who created them? Donors. So the donors, they do what? They donate. Donate, man, they keep the electron away, and they become what? Positively charged. Very good. they become positively charged. Okay? And the electrons, they are free to go around, but still everything is neutralized. So those electrons, they have some electric force with those acceptors, donors, sorry. And still everything is neutralized, but you know, they are freely moving. Good enough? Let's keep going. Now, we call the acceptors on the p-type the bound charge. Why they are bound charge? First of all, they are charged because they have still an electron. They are negatively charged, so they are charged. And they are bound because they are already having bound with other silicons. Yes or no? They are not freely moving. That's why we call them bound charges. Okay? Good? Very good. And the same thing for the donors on this side. They are also called bound charge because they are bound inside the crystal of silicon and they are charged. They are ionized. Very good. That's it. So we need this description to understand what's going on with the PN junction. Alright. Let's go. After a little bit of storm, this is what happens. Woo. What's going on there? Oh wow, they disappeared in here. So basically here, that we have, what do we have here? We have an n-type semiconductor, yes or no? The majority are electrons, yes or no? Very good. Now let's look only at the electrons. The electrons on the p-type, they are majority or minority? Minority. Very good. So the density of the electrons here, the free electrons, is high or low? High. Compared to the electrons in here. So if there is a density change, where there will be, what that creates? Diffusion current. That's what we said, yes or no? Because there is a density. There is a density variation. There is a gradient. Very good. So because of that, then the electrons, they say, there is room there. Let's move on. And the diffusion, as I explained last time, it's exactly like an ink in a cup of water. So it diffuses. It's universal phenomena. It happens with anything that's freely moving. Gas, electrons, people, anything that can move. If there is a change of variation, means if any species find a space that is less occupied by themselves, they go. It's called diffusion. So these electrons, they move on the other side. So what happens with the holes here also? The holes here also, they have high density compared to the holes in here, yes or no? So the holes also, they decide, why not? There's a free space there. The density is low there, we are high here, let's go. Boom. So the electrons will move this way, the holes will move that way. That's good. But again, what happens? Oh, hold on a second. Just a second. Oh, this is to move forward, I want to move backward. Okay, good. So what happened is that as the electrons move on this side and the holes go move opposite to it, they meet each other at the junction. Hello, hi, how are you? Boom, they are combined. So they do what? They disappear, yes or no? Because we said that if an electron meets a hole, bye-bye both, they disappear. And we call that, what we call a recombination. Very good. So that's what happens. Very good. So with that recombination, so these guys, the bound charge, what happened to these bound charge? They lose their cover. They were covered by the electrons in here, and they were covered by the holes in here, yes or no? But those, they went there, and they are combined in here, so they're gone. It's like a mother who lost his son or daughter. Bye-bye. So we start to cry. So it's ionized now. So there's no cover for this unbound charge in here. And the same thing applied on the other side, on the other side bound charge. Okay? Boom. So in this case, what will happen? So basically, we will have a scenario where basically on this side and in this side, we have two different charges. On this side, we have uncovered what? We have uncovered the donors, yes or no? That are positive. And here we have uncovered what? The acceptors that are negatively charged. Uncovered معناته الغلاف اللي كان عندهم طار. الستر اللي كان سترهم رب العالمين بها راح. Okay? So now they become now uncovered. Now what they have? Now in this case, what we have positive charge on this side and negative charge on this side. This is similar to what? Yes? Very good. A capacitor is basically, look, this is a two-dimensional thing. That in fact you have a 3D, yes or no? There's a surface in here. There is a surface, yes or no? And there's a surface in here. It's like exactly like your friend said, a capacitor. صح ولا لا? So, now we have a capacitor. And that capacitor, is it charged or not? It is charged, yes or no? This is one charge, side of the charge, and this is the other side of the charge. Huh? So we have a charged capacitor. That means what we have, this capacitor has what? If it has... Yeah, that's right. Though that means that they have electric field in between them. That's okay. And if there is an electric field, there will be what? There will be voltage between them. Ah, very good. Now things are getting interesting. Huh? Very good. All right. Thank you very much. But there's more thing to say also. And that is what? Let's see what this star will bring us. Oh. I'm not going to read these things. You can read that. I want just to explain. What's here? No, I don't want that. So, yeah, so basically that's what happens. So basically what we have here, so now with a bound charge, we have basically an electric field in between. So we have a voltage between this side and this side. But again, do we have here a voltage between this side and this side? Why? Why there is no voltage between this side and this side? Means are the terminals here. Why we have only voltage in here? Why this voltage not up to there? Anyone? Raise your hand. Raise your hand. I need some people to... Okay, give you a chance this time.
Because maybe positive and negative bound charges are neutralized, like they say.
Nice try, but that's not the answer. Any candidate? Yes, you?
Because in this side we have positive and negative, and then we have, but in the middle we have only positive.
Close. I didn't hear the answer yet. Yes, go ahead.
Maybe both of them cancel each other.
It's true. Basically they have the same voltage. Yeah, delta V is equal to 0. But why we have here delta? Why they cancel each other? That's exactly the question. Again, nice try, but...
Because one of them is positive and the other is negative.
Which one is positive and negative? We're talking about this terminal and this terminal, huh?
I mean the
Where?
graph in the middle.
No, the graph is our graph. It's our understanding. Why we graph it like this? That's the question. So any try? Yes, go ahead.
Maybe the voltage exists only in the junction.
It is true, but why we don't have a voltage in between these terminals? Any try? Any try? Don't speak. Please raise your hand. Give the others a chance, okay? Again, let's give another one. Anyone? Okay, again? Yeah.
Maybe because the voltage is carry a negative charge and the other is positive.
Repeat, explain. Try.
Maybe the first one carry a negative charge.
Which one? We're talking about the terminals. I'm talking about this side and this side. I'm not talking about in between. That's it. What you're talking about? Khalas, then that's it. So any try? Go ahead.
Maybe we have electric field only inside.
Well, that's the fact. But why we don't have an electric field between these two?
Because it's same on both sides.
It's
same.
what's the same?
The-
Yeah, it's the same voltage here. So why we have the same voltage?
Because electric field push minus 3 to expand.
No. This is very simple. Go ahead.
I think because no charge.
Exactly, because there is no charge in here and no charge. Remember, this is neutralized and this is neutralized. Yes or no? That's what we said. So where the voltage or electric field will come? That's it. It's gone. Nice try. Very good. And that's the answer. That's why we can't really. This is very important in the lab. We cannot measure this voltage between the terminals. Why? Because there is no charge here or there. It's a very important thing. I'll show you a surprise about this in the next class. There's a very nice surprise I will show you in the lab. People, they think this class has no, how fun and hard. I will show you something really interesting, and I promise that you will like it in the next week class, okay? So yes, we cannot measure this voltage between this terminal and this terminal. That voltage exists only between these two because they are charged. Here, they are not charged. the terminals are completely neutralized. So they have the same voltage. Okay? Clear? Very good. Excellent. All right, good. So let's keep going. And this is basically just, you know, an extra reading for you to see how the distribution of the electric field and the voltage are in two parallel plates. Okay? And to see that the voltage here, or the electric field, does exist only in the capacitor, only in between the plates. If you are outside the plate, here at the very extreme and here at the very extreme, you can see it's a little bit green here, yes or no? So that means we don't have electric field. Okay? And there is no voltage in there. Okay? The electric field in the extremities here and here are zero. These are simulations. Okay? Alright? And for more reading, have a look at this. And how we simulate this, of course, using Poisson equation. That's it. We are not going to touch electromagnetics here. Otherwise, it will be a disaster for you. So, okay. So this is what happens at the beginning. Let's keep going. So boom, boom, boom. And then we create this bound charge in here and there. Very good. This area has absolutely no free carriers. Why? Because there's an electric field there. If there's anything, it would be cleaned out. We call this area depletion region. Depletion region. Right, is it written there? I'm sure that it will be written somewhere. But let me bring that smart notebook. Okay, I have to write something there for you. Okay, let's see. Okay, no. What do we mean by depletion region? Depletion, from the word deplete. Deplete means empty. Empty, empty. Okay? And so, okay, let me fix something, okay? Hold on a second, there is some issues going on. Duplicate. And then we'll do this. Some technical issues in here. Okay, thank you very much. So, I need this little one. Good. Oops, what is that? From here. So, very good. So, depletion is written like what? It's written there? But that's fine. I like to write. Do you like my writing? I know it's not that great, but depletion. From the word deplete. Deplete. Deplete means or depleted معناته مفرغ. Okay? In other words. Okay? Good. So in this region, nothing is shown after okay. So here then we will have no free carriers moving around. Why? The electric field will push them in one side or the other. But then before that I have to mention something really. That's also very, very important. So forward, this is back. Oops, let me check that. I have to go back to this. Technical issues here. Let's go back a little bit because I have to show something really interesting. Okay, good. So, if we talk only about the holes, for example, if we take the holes only, the current related to the holes. So the holes, the diffusion current of the holes will go where? Will go this side, yes or no? Yes. Very good. Now, the electric field that we have here in between, where does it go? To right to left or left to right? Right to left, from the positive charge to the negative charge. Excellent. So this is the electric field, it's going this way. Now, the minority carriers here in the n-type, electrons or holes? Holes, very good. So let's say one hole was going around here and suddenly jumped into this place because they are moving, huh? So that electric field, what does it take that minority hole? To the right? To the right or to the left? To the left, very good. So the diffusion current of the holes will go from the p-type to the n-type. But the minority, the holes that are minority in the n-type, the electric field will push them to the left. So holes coming here and holes coming that way. So they are against each other. صح ولا لا? If we take 1 to 1, it will be 0. صح? But it depends how many are coming and how many are left. Okay? Very good. صح. So the first one, the first component of the current of the hose here, the diffusion current, at the beginning, at the very beginning, were huge. صح ولا لا? So too many holes coming into this. As soon as this electric field start to exist, it will try to push the holes that are minority here to the other side. The first current is going to be the diffusion current, but the second one is going to be what? Drift current. See? So the drift current is opposing the diffusion current. The more or the bigger or the more hose comes from the p-type to the n-type, the more uncovered charges become. Yes or no? So the more uncovered charge, the bigger the electric field. Yes or no? Now the bigger the electric field, also the more hose will be sent back from the n-type to the p-type. So we have two competing currents. The first current is the diffusion, and the second one is the drift, and we use the IS. We will use it later. We call it later the saturation current. That's why we call it IS here. And these two, they are opposite to each other. Okay? So at the beginning, this current was huge. Yes or no? Because there's no electric field at the beginning. Yes or no? As more holes move there, the electric field here will grow and grow and grow. And this electric field will basically create saturation currents that will make, actually, this electric field will try to stop, first of all, these holes. Because the holes, when they are coming this way, they find the electric field. Yes or no? That electric field also will try to push them back. Yes or no? Because there is an electric force. Yes or no? Yes or no? And the holes will move in the same direction of the electric field. So over the time, what happens is that, let's see. So over the times, they will try, I mean, it's not, I don't know why it's not shown there. Over the time, this diffusion current decrease because of this electric field, until that diffusion current will be equal to the drift current that is sent, of the hose coming from the n-type back to the p-type. And that's why at the end, at the, what we call the thermal equilibrium, when things get constant, that diffusion current that decreased over the time will be equal to the saturation, and the total current will be equal to 0. So nothing will move around. Okay? And that makes sense, because otherwise, this diode will make what? Will make solar power or what? There's no there's no optical energy to come. So how come this current will stay forever? No, it doesn't stay forever. And this what makes it dead at the end, okay? Our thermal equilibrium. This will take very, very small amount of time. It's in the micro, even the nanoseconds, okay? So as soon as this happens, this current comes, the diffusion current will decrease over the time because of the electric field, until that diffusion current will be equal to the drift current that is generated by the electric field of the depletion region, okay? And at that time, the total current will be equal to 0. This applies to both the holes as well as the electrons. What we study here in the holes applies also in the electrons. And you can do that at home, okay? So it's absolutely applicable there. And the total current of the whole thing will become 0. So at the end of the day, at the equilibrium condition, when things get settled, what will happen? We will end up with just a junction. And across that junction, we will have a depletion region. There's a voltage in there. And these guys stay where they are. And these guys stay where they are. And everybody is happy where they are. Okay? And this depletion region, this electric field that is in here, it is stopping the phenomena of diffusion for good. No more diffusion. Because otherwise, technically speaking, it should continue. But this electric field is stopping that. It's stopping the holes from going from the p-type to the n-type, and it's also stopping the electrons from going from the n-type to the p-type. Clear? Any question? Any question? Now, I have a question. That voltage that we have in here, that question will come later, depends on what exactly? That's what we are going to see in the next few slides. And that voltage, we call it the barrier voltage. Why? It's barrier. It's like SID, okay? It's stopping something, okay? So that voltage, the barrier voltage, we call it the electric barrier voltage, V0 or V0, is equal to this equation, thanks to the physicists, scientist people. They found out the formula for this barrier voltage is equal to Vt. What's Vt? It's written there. Equal to what? Yes?
K times temperature over Q.
Over the charge. Very good. I have missed something last time. We studied it also last time, but I didn't mention it, but I have to mention it now. Vt is equal to what? Where did we mention Vt, the thermal voltage? Where did we mention the Vt, the thermal voltage? Raise your hand. Don't talk like that. I need some hands here. By the way, participation will count at the end. I will also develop a paper with me and will know names and add them myself. Okay? So better participate during class. Yes, at the end. Vt, we mentioned it when? When did we use Vt? Yes, diffusion. But that's half of the story. What's the other half? Vt is equal to what? We know the equation, صح? So where did we talk about it? Yes, at the end?
Relationship between diffusion and
Diffusion what? Diffusion what?
diffusion
Constant.
constant.
And what else? Have a look again. And then?
Mobility.
Very good. Try to revise. I'm asking you for the last time. If you don't revise, you are asking yourself to. So yes, so the Vt, the thermal voltage, is the ratio between the diffusion constant D over the mobility. So the thermal voltage here, okay, let's, sorry about that. We have to go back actually. So let me write it down here for you. Let's have fun, some fun, okay? So, let's see. So Vt was equal D, diffusion constant, over what? The mobility. I don't care. You can call it N or Mn or P. It's not a big deal, It's not really a big deal. It applies for holes and electrons, the same thing. Thanks to Albert Einstein, who found this formula. But the idea is not there. What I said here is that this Vt is actually Kt over Q. Yes or no? That means if we increase the temperature, we increase this ratio. صح ولا لا? We increase this ratio. That means what? That means we increase the diffusion parameter. Or we decrease also, or maybe and or, could be both, could be one of them. And that's what's very important fact, that when you increase the temperature, the diffusion always increase. Always. And the mobility actually also decrease. Why? Because when you increase the temperature, the electrons, they will bounce too much between the atoms. They will not have enough time to move. You understand? So bounce, bounce, bounce. So their speed, their velocity goes down too. Yes or no? Because they bounce with many atoms, they are coming in the path of them and trying to stop them. Okay? So that means their velocity also will decrease. So thanks to this formula, which is really remarkable formula, that relates the diffusion phenomena to mobility or to drift phenomena, and that speaks very loud. When you increase the temperature, the diffusion phenomena increase, and that's a fact. If you want to diffuse, and that's happening also in microelectronics fabrication, when you increase the temperature, you actually move the diffusion faster. I will show you that in maybe next week. The mobility also will decrease, as I said, because the crystal will vibrate too much, and the bouncing will kill the mobility or the speed of what? Of the holes or the electrons. Now back to our business. Our business says the following. So V0 is equal to that Vt, logarithm Neperian of Na, acceptor's density times the donor's density, divided by Ni squared. One of you, she was clever enough to watch the video and answer the question that I'm going to ask you now. With increasing temperature, V0 will decrease or increase? Who said increase? Raise your hand. Increase. V0, when we increase the temperature, does V0 increase or decrease? Who said increase? Raise your hand. Who said decrease? Raise your hand. The majority, they are not with these, not with those. صح ولا باقي? What happens?
No.
Not sure? Choose. Well, okay. Who said the increase? Say why. Who said the increase? Explain. That's fine. The increase? صح. Why?
Because from the relation of VT, the temperature increase, the VT will increase, and according to that, P0 will increase.
صح. Straightforward. Thank you very much. صح. This is constant or does it increase with temperature or not? صح. With this one, ND. صح. NI. Oh, let her speak. Dabi, just watch her. NI, does it increase or constant?
It will stay constant.
Oh, really? So tell me what's NI?
The NI concentration of the...
What's called?
The
Intrinsic. I will help you. Intrinsic.
Yeah, intrinsic and of semiconductor.
The intrinsic density of the free carriers in the semiconductor. Ah, very good. And that density of free carriers in semiconductor, it basically is the density of free carriers that are created by breaking the bonds.
Yeah.
Ah, very good. Does it depend on temperature or not?
Yes.
Yes or no?
Because if we increase,
So, does it increase or decrease with temperature?
will increase because the bonds will be taken down.
Very good, very good. So, Ni will increase and it's also squared, yes or no?
Yes.
Saha, very good. So this ratio will increase or decrease?
Will decrease.
Will decrease, very good. So this side and this side logarithm.
Yeah.
So the logarithm of something decreasing will increase or decrease?
Decrease.
Very good. So this side of the equation will decrease and VT will increase. How can you say this one will increase? Who's gonna win? That's the question, yes or no? So we don't know who is gonna win, VT or the logarithm. That's what you need to know. Go and check, let me know the answer. Alas? Good? You understand? It's not trivial. Do you get that? So that's how we analyze the equations and how things moves. You look at the function, you play around with it, okay? It's exactly like a game. Very good. If you find the answer, let me know. And you may be lucky to get a bonus. And this is the first bonus of this course. Very good, very good, very good. So now, the current IS, which is basically drift or diffusion. Drift, yes, very good. It's a drift. Is composed of what exactly? So IS is a current of majority carriers or minority carriers? Minority carriers. Pay attention to this. Huh? You have to write it down if you want to. Remember, this is very important fact. So IS is the current of the minority carriers, both electrons and holes. Electrons in the p-type, holes in the n-type, okay? So the minority carriers are the constituents of this current. هم اللي يخلقوا هذا الكرنت، صح ولا لا؟ But those minority carriers, they depend on temperature or not? The minority carriers, they depend on temperature or not? Think about it, think about it. You have 1 minute, think. Minority carriers, they depend on temperature or they don't depend on the temperature. And why? If you say yes, why? And if you say no, why? Who has an answer? Yes?
I'm not sure, but
Yeah, give it a shot. I will not blame you. I will never say it's a bad answer. I will say it's wrong or correct. That's fine.
Okay, it depends on the temperature because
So.
it's made by broken bonds of silicon.
Very good, yeah, because minority carriers in an n-type or p-type, they are actually created by the broken bonds because the majority are created by the dopant. صح ولا لا? The minority are there. And the equation that is a proof of that, we study it too. Who knows the minority carriers in the n-type? Well, just a second. Who did revise last class or last week as well? Who did revise? Very good. So, the majority carriers here, they did not revise. So today's class is the minority carrier class. The others, they need to wake up before it's too late. Very good. So, the minority carriers, do we know their equation or not? Let's say with p-type. Let's talk about only p-type. P-type. Who are the minority carriers in the p-type? Electrons or holes. Wait. We are in P-type semiconductor. P-type, huh? P-type. Okay, let's see, huh? Let's do it with the huh? Let's see. Justice. Right, good. So this is a P-type, huh? No one talks to you in class except Abd al-Da'if. So this is a P-type. Okay? So the majority carriers there in P-type are what? Majority carriers, huh? Alhamdulillah. Or minority carriers are? Very good. Let's see. So how do we write the density of the majority carriers? The density of the majority carriers. What's the parameter? The majority carriers here are who? Holes? So how to write their density? Wait, raise your hand, huh? Raise your hand. Majority carrier density. What's the parameter? Raise your hand. I'm very disappointed. I see only 1, 2, huh? 3. 3. That's it. 3. Yeah? P? No, give me just the parameter. What's the parameter? How do we write? What's the parameter? Name. How you write the name? No, I'm talking only about the majority carrier. I don't ask you for the equation. How you write the density? How do you write it? Is it PP? Is it NN? Is it PN? Is it NP? Don't take advantage. P? That's good. So PP, P inside the P type, is equal to how much? These are majority, yeah? So, one minority, I need the minority. And minority here are who? In the P type? Is what? Electrons. So, how to write their density? Yes? NP. So, NP. NP is equal to how much? Who knows? Yes, over there? And I square over NA. Very good. I'm sure you have opened the slide now, right? Yalla, good, very good. So that means we said that. Remember that? We said Ni depends on the temperature, yes or no? And so NP will be. Sah wala la? Because this one is constant. Sah wala la? You got it now? Yeah. We explained it physically, but this is the equation to explain. What wala la? Very good. Now back to that current, IS, the drift current, is made of the minority carriers, whether electrons or holes, it doesn't matter. Both actually. And it depends on minority carriers, which depend themselves on temperature. So that means the temperature will also change IS, the drift current. Yes or no? Yes. If we increase the temperature, the minority will increase and this one will increase. It's a very important observation. Very important because it will come back to us later on. So this is very important. Now, the second observation here, it says that any depletion layer voltage, we are talking about which voltage here? The barrier voltage, yes or no? Because it happens in the depletion layer. Layer means area, or sath, or something like that, okay? That's what it means. So, any depletion layer, regardless of how small, the barrier is small or big, will cause the transition across the junction. معنى to any electric field will cause the transition anyways. Will cause what? It will cause IS to exist anyways. Then as soon as the depletion region exists, now any minority in that will be thrown by IS. Okay? So that means IS, it's not dependent on how big is the voltage. Only if it exists or not. Okay? So if there is a depletion layer, there will be IS that is independent of V0. That means if that barrier is high or low, IS is independent of that barrier. It will be the same. Whether the barrier voltage is high or low, IS will be the same. Okay? Maybe we'll revisit this later on as well in one of the classes. Alright, this drift current IS basically is the motion of the minority carriers. Very, very important thing, okay? Alright, good. So let's keep going. Oh, we have to go on this side. Okay, let's see. Where is this? Okay, let's see. Moving. Yes. Ooh. So, boom, 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 boom. So this is happening all in the open circuit case. We did not connect this junction to anything. Okay. So at the end, as I said, in the equilibrium, the diffusion current will be equal to the saturation current, and that's it. So everybody is happy. Well, now question. The depletion region, let's go back actually, let's go back. Here, you see, this is the junction. That means what? That means all this is the N-type and all this is a P-type. That means this part of the junction of the depletion region belongs to the N-type, yes or no? And this depletion belongs to the P-type. صح ولا لا? Now, is this with, is it the same as this? In other words, is it symmetrical, the depletion region, or not? That's the question. No? Who says symmetrical? صح. Who said not symmetrical? Majority of the others. We are talking about a drift student. Today is a drift student class. What about the diffusion student class? Sleeping? صح. Who said that this is symmetrical? Raise your hand. Tell me why. 1 second. Symmetrical? Raise your hand. It's okay to make mistake in my class. You know that, right? صح. Who said you? Why it's symmetrical?
Because we have equivalent.
Equivalent what?
The diffusion current and...
No. We are talking only about now. We are talking only not about talking about the currents. We are talking only about the depletion region. بمعنى آخر, we are talking about only the distribution of the bound charge. What are they? We are talking about this area, this size, this. See this size and this size. We're not talking about the currents anymore now. We're talking about this area, this volume. Remember, this is a volume. There's an area here like that. Okay, it's like this. So if I draw something here, if I draw, it's like this. Okay. So this is maybe call it P-type, for example, and this is maybe the N-type. Okay. So that area that I'm trying to tell you about is this area. Okay. Where we have absolutely nothing. Okay. Okay. This area, Okay. The whole area here. We call it depletion for a reason. Why? Because there's no free carriers. Yes or no? That's what I'm talking about. So now, the question is this symmetrical? معناه, is this side the same as this side or no? And why? Yeah, you didn't answer. Yes, go ahead. Yeah.
Not symmetrical, maybe
Why?
because the electrons is smaller than the holes in size. Maybe.
That's a good point. Yeah, that's a good point. It's basically not necessarily because maybe the density of these two acceptors in here is different from the donors in there. صح ولا لا? Then when there is a recombination, then we'll have one charge here, one charge here. Yes or no? But the density of the acceptors in here is not necessarily the same as the donors in there. Let's study that now together in scientific way. Okay? Let's do that. And let's do that how? Let's see. Okay, cool. Okay, so that's what I'm saying here. So typically we have these two are not always the same. But that's fine. So how we are going to study that? Okay, let's take some measurements. Okay, let's take some measurements. These are the results, but the measurements are not there. Let's go to the next slide. So let's take this side, we call it, it has a width of xn. So from here to there is xn. From here to there is xp. Why? Because this is the side of the N-type, yes or no? And this is the side of xp. We have added the minus just because we choose the x-axis to go from left to right. So that's why the index here, the coordinate here is positive and the coordinate here is negative. But in terms of distance, this is xn and this is xp. That's it. So now let's study that and let's see if we are on the same page. Okay, good. What we know for sure, if we take now a graph of the chart, So basically, if you here this axis is the axis of the density. We are talking about the density of the dopant on the dopant on the n-type, which is this side. They are what? They are positively charged. Yes or no? So that density will be positive. And the density of the dopant in this side, which are the acceptors, they are what? Negatively charged. So this is the density here, and this is density here. They are not exactly the same. So from here, from 0 to this value, is not the same from this 0 to this value. Yes or no?
Yeah.
But what we know for sure is that to know the total charge, we have to multiply this density by the volume. Yes or no?
Yeah.
So the volume will be what? The donors times, of course, Q, single charge, times the cross section, which is A, times the width, that is N. Yes or no?
Yeah.
You got it? Anybody has a question about this? So this is clear. Yes or no? The negative charge on the p-type on the other side, we are in the depletion. Here we are talking about the depletion. So here in the negative charge, the charge in here will be the density that we have in that side of the acceptors times the volume, and the volume in this side is also A times this distance xp. Yes or no? Times the density of acceptors. But what we know for sure is that the negative charge on this side is exactly the same as the positive charge on this side. Yes or no? So Q plus is the same as Q minus. Why? Because we said in the diffusion that an electron will meet a hole from the other side. So one electron goes from here off, one hole go from there. So they must, so the uncovered bound charge here will be exactly the same number as that. Yes or no? Sama wala la? So the same number because they lost, each one lost somebody. The donors or the n-type, they lost an electron, and the holes, the p-type, they lost a hole. So that's why we have Q plus on one side and Q minus on the other side. So, very good. Thank you very much. Let's keep going. So if we take this, this charge and make them equalized, so what will happen, sir? This is what will happen. This what will happen. A, we can cancel it from this side and this side. Yes or no? Q also will cancel from this side and this side. Of course, you have to take notes, because when you revise using video, it will be pain. Trust me, because it takes time to watch the video. So Q bye-bye, Q bye-bye, and A bye-bye, A bye-bye. So what we have, XP and A is equal to XN and D. Correct or no? Correct? So these two, they get cancelled from each side, so we have only this equal to this. Good enough? Now, we can write this equation of these two only, and write it in this equation. Yes or no? Because XP and A is equal to NDXN. XP and A, that is XP and A, is equal to XN and D. Yes or no? Very good. Now, if NA, the density of acceptors, is the same as that of the donors, this will be equal to?
1.
And in that case, XN will be equal to? And it will be what? Symmetrical. Now, what else? It will be what? It will be, let's go back. It will be this side, XN, the same as XP. Same width, yes or no? Symmetrical. The side of depletion in the n-type, same as the p-type. This is only when Na is equal to Nd. The acceptor's density is same as the donors. Very good. Now what happens, sir, if things are not that rousy? If Na is bigger than Nd, if this Na bigger than Nd, so it will make what? Xn bigger than Xp or less than Xp? Na bigger than Nd. So Xn will be bigger or smaller than Xp? Who say bigger? Raise your hand. Bigger. Let's see. Smaller? So why smaller? Because majority are bigger, so I don't know. Yeah, why smaller? Yes, you said smaller, yeah? Why do you think that Xn is smaller than Xp when Na is bigger than Nd? In Arabic, explain in Arabic, that's fine. ليش عكس؟ إذا كان هذا أكبر من واحد فهذا لازم يكون أكبر من واحد، صح ولا لا؟ متساويين. فمعناه إذا هذا أكبر من واحد معناه هذا أكبر من هذا. صح ولا لا؟ So if this is bigger than 1, because NA over ND would be bigger than 1, yes or no? In this case, huh? So it makes XN bigger than XP. Very good. Now, look, NA bigger than ND, يعني the p-type is heavily doped, yes or no? Is doped more than the n-type, yes or no? But XN, is XN in the p-type or the n-type? It's in the n-type. Let me write that in this board because that's better actually. So let's write. So XN over XP is equal to N. What? NA over ND. Yes or no? So I will choose the red for P. Huh? Let's see. NA they are in where? In P or N? Acceptors. They are in the P or N? P. So. And XN is it in N or P? And OXP in? And then the others, they are basically in the negative. Yes or no? See, if NA, let's say, if NA, I will write it in. So NA, if it is bigger than N and D, this implies that XN in blue bigger than XP. Yes or no? Correct? Very good. يعني if the P plus is heavily doped, then if the P type is heavily doped than the N type, that's what it means. Then the depletion region will be wider in the N type than the P type. Yes or no? This is what it means. Here, if the P type is more doped than the N type, then the depletion width in the N type must be bigger than that one of the P type. So, very good. What does it mean? Let's go back and let's have a look. No, not this one. Let's go back very quickly and check. Oh, we are doing in time. Almost there. So that's what it means basically. So that means, if we look here, if the donors, if the acceptors means these ones, they are heavily doped, that means crowded of donors here. Here we have few of acceptors. Then the depletion region here, XN, will be bigger than this one. Do you understand? So it will be wider in the area that is less doped. This is the conclusion. This is the area that is less doped, and therefore the depletion region will be wider in that side compared to the area or the p-type or the semiconductor that is less doped, that is heavily doped. So the more doping you have, the less depletion you have. The less doping you have, the more depletion you have. Okay? Inversely related. Any question? You need to revise again. Nothing comes for free. Okay, good. Let's keep going. Now, if we take those equations and play around with them, that's fine. With the one that I gave you, you will find this set of equations. W is basically Xn plus Xp. That means it's the width of the depletion region. The total width is going to be equal to this equation, and as you can see, is proportional to V naught, which is what? The barrier voltage. Xn is going to be, we can write it from this equation, is equal to W over NA over NA over ND and XP as well. But this is the most important fact here, is that the higher the barrier voltage, the bigger is the depletion region. Makes sense. So that's what it is. Okay? Very, very important equation. Now, now we talk about the charge, Q plus and Q minus. The same way that we studied before, we can find that the junction charge, which is the same for the positive and negative, we can write it in this equation, and that says the following. If the junction width increased because the barrier increased, then automatically the charge has increased. Or in other words, if we increase the charge of the depletion region, it will increase for me the W. Do you understand? The width of the depletion region. It absolutely makes sense, of course. the width of the depletion region will never increase if the charge does not increase. That's what it means. This is if we replace W with this equation that we just studied, it will give us this equation. Don't worry, these large equations, I will provide them in the exams. So it's just what we need to know is how they work. That's what I need you in this course. How to use the equations, not to memorize the equations. All right, this is basically the summary of what we studied. Okay, what has been learned in the PN junction. I let you read this very carefully at home. This is just a summary. Okay, so please have a look at that. Okay, we've studied also the bound charge and the diffusion current ID as well as the IS. Okay, and we said that the depletion region, that the depletion region is basically the area where we have no free carriers there, and is proportional to V naught, which is the barrier voltage that has been created at the junction. The higher V naught, the bigger will be this depletion region. Okay, and that V0, okay, which is the depletion voltage or the barrier voltage, is that it was created because of the diffusion current. If that diffusion current did not happen, V0 will never exist. Okay. Okay, and what else? Then we talked about the other current, that is the drift current, IS. We said that IS is basically generated or is made by the minority carriers that are thermally generated. Why? Because of Ni. What's that equation? We wrote it here in this page. Okay, and we studied it last week and last class as well. Okay, good. That's it. So that current IS, again, it's very important to notice that it's made of the minority carriers that are thermally generated, and that at equilibrium means everything when it settles down, this diffusion current is going to be equal, will decrease until it becomes equal to the saturation current or the drift current. We call it now the drift current, but later on we will call it the saturation current. All right, what else? Woo! Bye bye. Let's solve some problems. Let's solve some problems. Who has the book? Who has the book? Raise your hand. Well, show me the book. Who has the book? Show me the book. You have the book there? And the others? Watching? How can you, you have to bring the textbook. Or the chapter of the textbook, because it's heavy, yeah? Very heavy, I know that. You take only the chapter. Take the chapter, go to the library, he will step in for you, bring it with you, okay? If you want to succeed in the class, you have to bring it and you have to use it. Okay? Good, let's follow this. So we have a PN junction. And it is in equilibrium, means what equilibrium? PN junction equilibrium, raise your hand. We just said it, huh? لا حول ولا قوة إلا بالله. A PN junction in equilibrium means what? Raise your hand. صح, you? Yeah? Very good. That diffusion current is equal to the saturation current. So everybody is settled. And at room temperature means at T is equal to 300. So, the anode, where do you find the anode? Is it P-type or N-type? P-type. Very good. Is doped with Na. Na is what? Na is what? Again? Acceptors density. Yeah, density of acceptors. 10 power 18 per centimeter cubic. Without this unit, that's it. Nothing in physics or engineering without unit. And the cathode, which is the P-type side, okay, has the donor's concentration. It's this way. So, and the cross section is given to us 10 power minus 4 centimeter square. So, calculate PP and P0. Okay. Let's do that. So, can we do it in 2 minutes? Let's do that. Okay. So let's see. So let's start with the majority carriers. Okay, N, P. Sorry, is it the majority carriers? No. Sorry about that. So then P, P. PP is equal to how much? NA. Very good. And we have the number. So, and then NN is equal to how much? ND donors. So, now PN. So PN is what? PN, what does it mean? PN. Raise your hand. PN is what? Oh, raise your hand, raise your hand, raise your hand. I'm very sorry. Go ahead. Yeah, you.
Minority and entirety.
Minority.
Careers and entirety.
What are these minority careers? Oh, very good, excellent. Is equal to how much?
N I square.
Ni square, yes.
And D.
Very good, excellent. We have both. Ni is given to us? Yes, given. By the way, we didn't mention that. And you can calculate this one using the equation I've given you. This one, here. Here, on this side, okay? It's given there. And you can use also the equation I've given you before. So, and what about the last one would be? N, P, opposite to that, is equal to, almost, Ni squared divided by N, and A. Very good. That's it. We have everything there, right? Very good. And W and X and XP, the one that we studied today, you can apply the equation I've given you today. Okay? Do that. Have fun. See you next week, inshallah.